Okay, so I'm going to do lecture 13, example 2, which is a boundary condition problem. So the idea of this problem is that we have two different media here, right? So we have medium 1, which is on the left side of this boundary. We have medium 2, which is on the right side of this boundary. And what they give you is that in medium 1 we have a relative permittivity of 2, in medium 2 we have a relative permittivity of 5. So what we want to find out is two things. One, what does the electric field intensity look like whenever we cross the boundary? So we know we cross the boundary, maybe it's going to change its, well, it doesn't look like that much of a change, but it's going to change its magnitude and its direction. So let me draw it so it's a little more drastic. I don't know exactly what it's going to look like yet until I solve it. Maybe it looks like this. Okay? So what we need to find out is we need to apply our boundary conditions to find out what is E2, right? So we know E1, we want to find out what is E2, and then we want to find out a second thing. We want to find out what is the angle made here. So we'll call that theta 1. And the angle here, well, that theta 2. Okay, so we want to find the angle that the fields make with the boundary. Okay, so we look here and we say we have E1. Okay, and we know that E1 is composed of two components. One component which is tangential to the boundary, and one component which is normal to the boundary. Okay. So if we can find them, we can use them based on our boundary conditions to find out what E2 is, okay? So let's find this out. So we can see the boundary right here is normal to the z-axis here, right? So the z-axis is going this way, right? So the boundary is going to be normal to the z-axis. So it's pretty clear to see that the normal direction is going to be in the AZ direction, right? The normal vector will be the AZ vector because it points in the direction of the z-axis. So with that being said, you can just visually inspect this equation right here and you can tell that the normal component is just going to be the z component, right? Because that's the only part that's normal, right? So we could say that En1 is equal to 5 AZ. Okay, En1 is equal to 5 AZ. Okay, so if we look at that equation right there for E1, we can find out what ET1 is, right? So we could just take ET1 and we say it's basically E subtracting off the normal component, right? So we take E, which is that, and subtract 5AZ off it, we get what's left, which is 3AX plus 4AY. Okay? So this is our tangential component, and this is our normal component. So this normal component right here is going to be 5AX, and the tangential component, which is this right here, would be 3AX plus 4AY. Okay? Okay, so now we can use our boundary conditions. And we could say, well, we know that boundary condition 1 says that whatever the tangential component of the first one is going to be the exact same thing as the tangential component of the second one. So they're not going to change at all. Okay? So that means that the tangential component of the second electric field intensity is going to be 3AX plus 4AY. So we know they're exactly equal to each other. They always will be equal to each other no matter what. Okay? So this component right here is going to be the same as that component right there. Okay? But now we have to find out what is the normal, okay? And we know that the normal is going to be, well, the difference of the normal components is going to be equal to the surface charge density. However, in this problem, it mentions nothing about there being a density of charge on the surface, so we'll just assume that rho sub s is equal to 0, okay? And if we know that rho sub s is equal to 0, this is a special condition of the boundary of a boundary condition. And we'll say that this means that the electric flux density of the first is going to be equal to the electric. So we see that because there's no surface charge density, these two electric flux densities are equal to each other. So this means that epsilon R1 epsilon naught E1 En1 is equal to epsilon R2 epsilon naught En2. Okay, and we see that the permittivity of free space cancels off for either one. So then solving for En2, we have that En2 is equal to the ratio of the relative permittivities times En1. So this would be 2 divided by 5 times 5, right, which just gives us 2. Okay, so that's, notice it's just the magnitudes. We're just solving for the magnitude. So we want to actually get the vector component. En2 would just be equal to 2 in the normal direction, AZ. Okay? So now we have the normal component, we have the tangential component for E2, and we'll say that E2 is equal to the tangential component, which is 3ax plus 4ay plus the normal component, which is 2az. Okay, so we can say that this here would be 2az. This would be 3ax plus 4ay. Okay, so now to get the angles, we need to find the magnitude, the difference of the magnitude of that vector and the magnitude of this vector. So you should notice here that we make a right triangle. Okay, we make a right triangle here, and we're trying to find this angle. So if we're making a right triangle, we should see that for this right triangle right here, this angle theta, this would be our adjacent side here, and this would be our opposite side. Okay, or this rather would be our hypotenuse, and this would be our opposite side. Okay, so to find the angle here, all we would do is say theta is going to be equal to the adjacent divided by the inverse tangent of the adjacent divided by the opposite. So it's basically going to be the tangential component divided by the normal component. Okay, but notice here that these aren't vectors, but rather these are magnitudes. Okay, so the tangential component is going to be the actual length of this guy right here, and the length of that right there is going to be equal to 4 squared plus 3 squared square root. Okay, and this, the length of this obviously is equal to 5, right? So we should say tan inverse of that right there. Okay, and when we calculate that, we get that that's a 45-degree angle. Okay, now from the opposite side, you can see here that we're taking the inverse tan again of the opposite divided by the adjacent. The difference here, so that's theta 1, so theta tan 2 is going to be tan inverse of the opposite, which is this 3ax plus 4ay. So that's going to give us, again, 4 squared plus 3 squared square root. But then the length of the tangential now is only 2. Okay, so we take the inverse tangent there, and we get 68.2 degrees. Okay, so what we did here was we used the boundary conditions, right, to know that the tangential component of the vector on this side would be the same as the tangential here. Boundary condition number 1, right, so that's how we solve for ET2. And then we used boundary condition 2, which says that the difference of the electric flux densities has to be equal to the surface charge density. But since we know it's equal to 0 here, we say they're set equal. From that point, we go down, we solve for En2 by using this condition here and the permittivities, and then we can simply calculate the angles that these make with the boundary there, just by using some trigonometry. Okay, thank you.